So to prove this, we want to make two other small, very innocuous assumptions. So this is assumption number 1, which is linear separability with gamma margin. We are going to make two more assumptions, but as you will see, these are not really assumptions, they are just simplifications, so to say. The second one is what is called as the radius assumption. So we can work without the second and the third assumption that I am going to put down and still prove convergence, but it might make things easier to work with if you make these assumptions, right. So the math becomes slightly easier to analyze. I mean, otherwise you just have to carry on a few extra terms which we are trying to avoid. So what is the radius assumption? The radius assumption says that for every point in my data set, the length of the Euclidean norm is at most some r, radius r, right. So for some r greater than 0. Well, all this is saying is that you have a finite data set and all the data points fall within a ball of some radius r. This is obviously true, because if you have 100 data points, there is one data point which is going to have the highest length, and now if I put a Euclidean ball of radius equal to the length of that data point, then all the data points will fall within that ball, right. So for example, if I had a data set like this, maybe I have a bunch of points here, 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 maybe there are some red points here. Now I can look at the length of each point, and then I will realize that in this particular example I have taken, this guy has the longest length. So which means that if I put a Euclidean ball of radius equal to this guy's length, of course I have not drawn the ball carefully, but yeah, so if this is r, then it means that all the points, the length of every point will be less than or equal to r, right. So by definition, because I have taken the largest point, so I am just assuming that there is this r, right. So for any finite data set, this is going to be true, right. So this is what is called as a radius assumption, just that there is a big ball of radius r within which all my data points are, right. So this is assumption number 2. Well, more than assumption, it is a simplification. The third one is also a simplification, but it needs a slightly careful understanding. Without loss of generality, we can assume norm of W star is 1. Well, what is W star? Well, W star is this guy which separates my data set with margin gamma. Now I am saying that W star's norm is actually 1. Now what does this even mean, right? So it means the following. So again, we have this data set where, let us say, we have this positive points, and then there are these negative points here, and let us say we have a W which is like this, which separates the positives from the negatives using some gamma margin, which means that I have this, maybe I will put a positive point here. Now this is a W, and this is the set of all x such that W transpose x equals gamma. Of course, this is the set of all x such that W transpose x equal to minus gamma, and all my data points are on both sides. But now I observe that this W's length is not 1, right. So maybe let us call this W star, right. So this W star's length is not 1, because the set of all W's whose length is 1 is, let us say, somewhere here, right. So maybe this is the set of all W's with length 1. Now what I am saying is that, well, if you give me a W star such that it separates my data set linearly with some margin gamma, now I can find another W star whose length is 1, which also separates my data set linearly with some other gamma which is still not negative, not 0, right. So where is that gamma? Well, I can pick that gamma, that W star in the same direction, but then if I just normalize it to have length 1, now think of this as my new W star. Let us call this W star hat, maybe not hat, I will just call this W star dash. Now what is W star dash? Well, with respect to this W star dash, well, with respect to the original W star, this line's equation was W star transpose x equal to gamma. Now, if I do W star transpose x divided by norm W star on both sides, well, norm W star is a positive quantity, so I can, that will not affect the equation still stays the same. Now, but then what I can now do is, it is the same line, but now I can write this as W star by norm W star transpose x equal to gamma dash, where gamma dash is gamma by norm W star. So, basically the gamma is rescaled, I got a new gamma dash, and now with respect to, now if I rename this W star by norm W star as W star dash, now this transpose x equal to gamma dash. Remember, it is the same line, I am not changing the line, I am changing the equation of the line by scaling on both sides. It is like saying that if y equals mx plus c is my original line, then so is 2y equals 2mx plus 2c, right. So, I can multiply 2 on both sides, that does not change my line, it is still the same y equals mx plus c line, right. But now, what I am saying is that in this particular case, because I have divided by norm W star on both sides, the line is the same, but now with respect to this renaming, I can write the same line as the set of all x such that W star dash transpose x equal to gamma dash. It is a new W star, it is called W star dash, and the gamma has changed to gamma dash. It is the same line, gamma dash is still a positive quantity, because originally gamma was positive, I divided it by a positive quantity, still a positive quantity, but the advantage of doing this is that this new guy that I have now has norm 1, which means that, you know, if you give me a W star which separates my data set with some gamma, let us say gamma is 10, now I can create another W star by rescaling your W star to make sure it has length 1, and the gamma will rescale accordingly, right. So, but still I now have a W star whose length is 1, which also linearly separates this data set with a different gamma. But because we did not make our assumption 1, just said that there is some W star with some gamma greater than 0, it did not tell me that gamma has to be at least this much or anything of that sort, right. So, we allowed for any gamma greater than 0, now we are still satisfying this assumption, right. So, which means that without loss of generality, I can assume that W star, the length of my W is actually 1, right. So, because for every W star that linearly separates my data set with some gamma, there is an equivalent W star dash whose length is 1, which separates my data set linearly with some other gamma dash, right. So, I can assume that the W star that is given to me is as well of length 1 itself, right. So, this is without loss of generality. So, now with these 3 assumptions, linear separability with gamma margin, which is the most important assumption, the radius assumption and the length assumption, we can now go ahead and try to analyze the proof of the perceptron algorithm, which we will do next. Okay, so let us analyze the perceptron algorithm with our assumptions that we have put down, right. So, analysis. So, what we are going to analyze is, we are going to look at how many mistakes this algorithm makes. Right. So, the way we are going to prove that this algorithm actually converges is using the following method. We are going to say that the perceptron algorithm cannot make more than a certain number of mistakes, maybe that number is 10,000, right. So, we are saying that the algorithm cannot make more than 10,000 mistakes, which means that after it makes 10,000 mistakes, right. So, it cannot make any more mistakes. What does it mean to say it does not make any more mistakes? It correctly classifies all my points in my data set, and so the algorithm would have converged, which means that if I can get a bound, a finite number as a bound for the number of mistakes the algorithm makes, then that implies that the algorithm has actually converged, right. So, which is what we are going to try and do now, right. So, can we analyze the mistakes of this algorithm? How many mistakes will this algorithm make, right. So, why do we care about mistakes? Because the algorithm only makes an update when a mistake happens, right. So, now observe that an update in the perceptron algorithm happens only when a mistake happens. So, now let us say we are at some point in the running the perceptron algorithm. We are given some data set, we are running the perceptron algorithm, and let us say at some point WL, or maybe I will put the L above, WL is the current guess, and a mistake happens. So, with respect to some data point x comma y, right. So, I found a point where WL is incorrectly classifying. So, the moment I find a point where it incorrectly classifies, I will update WL to WL plus 1 as WL plus x into y. This is my update rule, I know this, right. Now, if you observe, what is happening is I am adding a new point to my current old WL, right. So, now what we are going to look at is we are going to ask how much is the length of my WL plus 1 growing, right. So, I am updating my W by adding some point, right. So, x times y, of course, there is a label also which is 1 or minus 1, nevertheless, I am adding something to my old data point. So, how much is my length of my WL plus 1 growing, right. So, I can try to understand that quantity, right. So, let us say I want to understand that quantity, and we will see why that is a good quantity to understand. So, we want to understand what is the length squared, let us say, of WL plus 1. This is of course the length squared of WL plus x times y squared. But what is the length squared? This is the norm squared of a vector, which we know can be written as WL plus x into y transpose WL plus x into y, which is on expansion you will get 4 terms, which is WL norm squared plus 2 of the terms will be the same, which is 2 times WL transpose x into y plus x transpose x, which is norm x squared into y squared. This would be the expansion. Well, what is y squared? Well, y squared, y is plus or minus 1, so y squared is always plus 1. So, this whole thing is going to be just norm x squared. But now how big can norm x square be, right. So, x is any data point in my data set, and now I am trying to understand what is the norm squared of x. But we made an assumption about the algorithm. I mean, one of the assumptions that we made before we started proving was the radius assumption, which said that the length of any data point is at most r. It is within a ball of radius r, which means the length squared of my data point is going to be less than or equal to r squared. So, the third term is at most r squared, because norm of x is less than or equal to r by our assumption. Now, what about the second term? Well, it is 2 times WL transpose x into y. Now, what can we say about this term? Pause and think about this. This is a very interesting question to think about. What can you say about WL transpose x into y? Well, what happened with respect to WL for the point xy? Well, WL made a mistake for xy. That is why we are updating it to WL plus 1, right. So, which means that WL is making a mistake for x comma y means what? Well, the sign of WL transpose x and the sign of y, which is plus 1 or minus 1, they do not match. Either WL transpose x is positive and y is minus 1, or WL transpose x is negative and y is plus 1. Which means if I multiply these two quantity, right, so then it necessarily has to be the case that because WL makes a mistake on xy, their product cannot be positive. The product has to be less than or equal to 0, right. So, this guy has to be less than or equal to 0 because mistake. The update happens only when there is a mistake. So, this guy has to be less than or equal to 0. So, then we can say we can upper bound the whole thing by the norm of WL plus 1 squared by norm WL squared plus R squared. Because this is less than or equal to 0, I can throw away the term and just say that this is less than or equal to just the first term plus the third term, which we know is less than or equal to R squared. So, now what is this telling us? This is telling us that I have a WL, I make a mistake, I change my WL to WL plus 1, and now this new WL plus 1's length squared can grow by at most the previous length squared plus R square, right. So, it cannot grow more than that. That is what this is saying, right. So, it can grow at most by r square. But now interestingly, well, how did I get WL in the first place? I got WL because there was some WL minus 1, and now I made a mistake with respect to some data point, and so I updated it to WL, which means the same argument should also apply to WL, right. So, which means that I can say this is less than or equal to WL minus 1 plus r square, this term, of course, plus r square, right. So, WL plus 1 squared is at most WL minus 1's length squared plus r squared, right. So, because WL came from WL minus 1 and its length grew by at most r square. Now, WL minus 1 came from WL minus 2, and then I can inductively keep going behind till I get to W naught. But if you remember, Perceptron's W naught, the initialization was just the all zeros vector, right. So, which means that this can keep going, and then I can say that this is less than or equal to W naught squared plus L times R square, which is less than or equal to WL plus 1's length squared. But W naught square is just 0 because our initialization of W naught was just 0, right. So, this just tells us that, which implies what we are saying is that after you make Lth mistake, right. So, in some round you make some Lth mistake, you are the length of after making L mistakes, the new W that you end up is at most L times R square, right. So, this is one observation 1, right. So, we are saying the length cannot grow by too much, it can grow only by L times R square of WL, right. So, of the W that we are maintaining. So, now remember this L, makes an appearance here. That is the interesting part here. L is, remember, L is the number of mistakes that we have made so far, right. So, we have made L different updates for our W, and so that is the number of mistakes that has happened, right. So, this is mistakes. So, somehow we are converting our length of W into a bound on the number of mistakes that we have. Of course, this is not enough to say the number of mistakes of Perceptron is bounded, because we are only bounding the length from one side. We need to bound it from the other side also, which is what we will try and do next. From the other side, to understand the same quantity from the other side, we want to use the fact that there is some W star which linearly separates our data set with gamma margin. That is the assumption on the data set that we have. We have not used that assumption yet in this argument, right. So, the way we are going to think of that is that I have WL plus 1, which is my new W after WL makes a mistake on x comma y, and now I want to understand how does this WL's dot product with the W star look like. Remember, W star is something that I do not know, because that's an assumption that I am making about the underlying data set, that there is a W star which separates this data with gamma margin. I do not know what this W star is, but I know that there is some W star. So, I can still reason about such a W star. What I am trying to reason about is, as my data set, as I make mistakes in Perceptron, I keep changing my W, and I am asking how does my dot product with the W star change. We know that this is WL plus x times y, because WL made a mistake on x, y, transpose W star, which is just WL transpose W star plus W star transpose x into y. Now, what can I say about W star transpose x into y? Well, what is this quantity? Well, W star transpose x is the dot product that W star, the optimal W, makes with respect to my x, and then I am multiplying it with the label. Now, what is the property of the optimal W? The optimal W in fact separates my data set with gamma margin, which means by definition W star transpose x into y should be at least gamma, right. So, this guy is greater than or equal to gamma, where gamma is some positive quantity. This is an assumption that we have already made, right. So, that is the property of W star. So, now basically what is this saying? This is then saying that WL plus 1 transpose W star is greater than or equal to WL transpose W star plus gamma. This is kind of telling us that the previous dot product with the optimal W star has to grow by at least gamma once you make a mistake and update WL to WL plus 1, right. So, WL plus 1's dot product with W star should be at least gamma more than WL dot product with W star, right. So, which means that I can do the same argument now for WL, because WL again came from WL minus 1, the previous mistake happened, and so I updated WL minus 1 to WL, and so that should have given me an extra gamma boost to my dot product for with respect to WL minus 1, which means this is greater than or equal to WL minus 1 transpose W star plus gamma plus this gamma. This is this gamma, this guy is greater than or equal to this, same argument, right. And now we can keep going and then say that WL plus 1 transpose W star is greater than or equal to W naught transpose W star plus L times gamma. But W naught we know is just the 0, all 0 vector, right. So, this dot product with any W star is going to be 0. So, this is just the 0, this quantity is 0, which means what we have is WL plus 1 transpose W star is greater than or equal to L times gamma. This is 2. What it is saying is that as I make mistakes, my dot product with W star keeps increasing, right. So, and I know already from previous argument, as I make mistakes, my length of WL plus 1 cannot grow by too much. Somehow we need to relate these two things, right. So, on one side we have a upper bound on the length squared of WL plus 1, on the other side we have a lower bound on the dot product with W star, right. So, how can I combine these two things? Well, we can combine this if we can get a bound on the dot product with W star as a function of the length of WL itself, but that is not too hard to do, right. So, for any x comma y, and let me put this in a different color. So, this is something that we should know for any x comma y, right. So, let us say we are in some direction y, and then we have an x here. Now, if you remember from our PCA discussion earlier, right. So, if I take the projection of x onto this direction of y, if this is a perpendicular vector, this makes a 90 degree in 2 dimension. So, now this point which is like a proxy of x on the direction of y, we know is just x transpose y divided by norm of y into y, right. So, this is some constant times y, and that constant is just x transpose y divided by y transpose y, norm y squared, actually norm y squared. So, now this point is this vector, right. So, now we know by Pythagoras that this length is less than or equal to this length. Why? Because Pythagoras says that the length of the hypotenuse, length squared of the hypotenuse is the sum of the length squares of the other two sides, right. So, which means that this length squared, right. So, the length squared of this guy, this length squared is less than or equal to the length squared of x itself. This is Pythagoras. Of course, Pythagoras would say that this is plus the length squared of this guy, but then we can ignore that and say that this is less than or equal to this. But what is this? If I unravel this, this is just x transpose y is a constant squared, length y squared divided by length y squared squared, which is length y power 4 is less than or equal to norm x squared, which implies that x transpose y squared is less than or equal to norm x squared into norm y squared. So, basically for any x and y, what this is saying is that the dot product square is at most the length squared times the length of the x squared times length of y squared, right. So, this is, I mean, people might have seen this as a version of Cauchy-Schwarz inequality. So, this is true for any x and y, right. So, but now x and y that we care about is WL plus 1 and W star, right. So, we know already, right. So, from 2 we know that L gamma, right, is less than or equal to WL plus 1 transpose W star. I have just written it the other way, right. So, this is WL plus 1 transpose W star is greater than or equal to L gamma. Equivalently, L gamma is less than or equal to WL plus 1 transpose W star, which means that L squared gamma squared is less than or equal to WL plus 1 transpose W star squared. Now, think of this as some x and think of this as y. Now, this is x transpose y squared which by Cauchy-Schwarz would, our previous argument, has to be less than or WL plus 1 squared times W star squared, right. So, this is from Cauchy-Schwarz. Now we use our assumption that we could have always picked my W star which has a gamma margin such that W star's length is 1, right. So, this length is just 1 without loss of generality. So, I can forget that, and then this just then says that norm WL plus 1 squared is greater than or equal to this, right, L squared gamma squared. This is my third point, right. So, on the one hand we have from argument 1 that norm L plus 1 squared is less than or equal to L times R squared, whereas from the other side we have norm WL plus 1 squared is greater than or equal to L squared gamma squared, right. So, which means that this guy is actually sandwiched between two terms, right. So, this is greater than or equal to L squared gamma squared, this is from 3, and this is less than or equal to L R squared, this is from 1. Now, this implies L square gamma square has to be at most L R square, because this quantity is kind of sitting in between these two terms, right. So, which means this has to happen, which now implies L is at most R square by gamma square. Now, this means what, right. So, this is kind of telling us what is L. L is the number of mistakes that we make in our algorithm, and now we are saying that this mistakes is bounded by a term which is R square by gamma square, where R is the radius assumption, the radius of our data, and gamma is the margin of the optimal separator, right. So, this bound is what is called as the radius margin bound. Right. So, what is this telling us, right? So, why do we care about this bound? This is telling us that the number of mistakes that perceptron makes is at most R square by gamma square, where R is the radius of our data set and gamma is the margin with respect to the optimal W star, right. So, this means that the number of mistakes is bounded because, well, why is this? Because gamma is positive, and so R square by gamma square is a finite number. If gamma was 0, which means that if we assume linear separability with 0, allowing gamma is 0, which means that we allowed points to lie on the hyperplane that separates the pluses from the minuses, then we are saying this argument would just say that L is less than or equal to R square by 0, which means L is less than or equal to infinity, which means the number of mistakes is less than or equal to infinity is a useless statement. But the moment we say that we do not allow gamma to be 0, that there is some W star such that gamma is strictly greater than 0, then we get a finite value as an upper bound, and so the number of mistakes that the algorithm makes is finite, and so the algorithm necessarily has to converge, right. So, this implies perceptron converges. So, just to summarize, what we are essentially saying is that we have an algorithm now which is based on a very simple update rule. When you find a mistake, just add x times y to your current w and keep going on. So, this is the algorithm, and now this algorithm will run until convergence. But what does convergence mean? Convergence means that you run the algorithm until you find a w that correctly classifies all our data points. Now, we are saying now that it will indeed converge, because the number of mistakes that this algorithm can make is bounded by a function of the radius and the margin. And if radius is of course something that you can calculate from your data set, which is a finite number, and if you assume that the data set has a W star with a positive margin, then the number of mistakes is bounded, and so the algorithm necessarily cannot make more than a bounded number of mistakes, which means that eventually the algorithm has to converge, right. So, if our data set satisfies linear separability with gamma margin, then perceptron converges in a finite number of steps. So, this is good news because now we have an algorithm which is a super simple algorithm and we know that it converges. It is useful to understand this radius margin bound and its implication carefully, and that is what we want to do next, because that will lead us to several other sophisticated algorithms a little later in this course. But the good news is perceptron converges, but then what does it mean to say with respect to the quality of solution that we get, and what does it mean to say that converges with mistakes less than or equal to r square by gamma square, right? So, what is the role of this gamma? How can we understand the role of this gamma more carefully, right? The role of the margin. So, these are things that we need to think a little bit more carefully about this perceptron algorithm, and that will provide us more insights into developing new algorithms, which we will see later in the course, right? So, at this point I would want to stop by saying that we have put down an algorithm which is a very solid algorithm, simple solid algorithm, which has guaranteed convergence. In fact, this is one of the first algorithms in machine learning with provable convergence guarantees. And inspired by these algorithms, there are two major branches of thought which led to two different types of algorithmic development whose base was perceptron. We will see both of these in this course. One is called the neural network, one is called the support vector machine, both of which have inspiration from perceptron and its analysis. And so, this becomes a very, very interesting and important algorithm to understand in a classical machine learning setup. Okay, so with this we will stop here, and then next time when we come again, we will look at what are the implications of the radius margin bound and how that will inspire us to develop more algorithms. Thank you.